measurement error problem, this would also lead to the internal invalid of the regression if there is a measurement error in terms of x. Okay, in the class you are introduced the terms classical measurement error, but you did not you have not seen too much mathematical derivation. So here I want to complementary to your lectures to explain some math to you. Okay, so first of all, if this is the true population regression equations and you measure x imprecisely by xi tutor, what will happen? Okay, in this case the population regression equation will become yi equal to beta 0 plus beta 1 xi tutor plus vi. Okay, and vi here would be equal to beta 1 times xi minus xi tutor plus ui. Right? If you don't believe, just plug in the value of vi into this and you will generate the original one. Okay, well, if you measure the xi imprecisely, you will result in this population regression equation. Okay, then whether this imprecise equation is okay or not, this is not okay, right? Because you can see that the relation between xi tilde and vi are not equal to 0. Here you can see that if xi tilde increase, vi decrease, they are negatively related, such that the causal inference is not valid. Okay, so let's see how to use mathematics to prove that in this case the estimator will be inconsistent. Okay, so let's assume xi is imprecise. It is equal to the true xi plus some error term wi, where wi has the zero mean with the variance sigma square w, sigma w square. Okay, and w is random. In this case, well, everyone know that the beta 1 hat, this would goes to beta 1 plus covariance of xi tilde, the vi tilde divided by the variance of xi tilde, right? This is just a standard equation. Then to calculate this number, this value, we have to calculate what is vi. Okay, here vi is equal to beta 1 xi minus xi tilde plus ui, given at the top. Okay, and xi minus xi tilde here is equal to negative w, given here. Okay, if you want to get xi minus xi tilde, you minus xi tilde to the right hand side and put the minus wi to the left hand side, you will get minus beta 1 wi plus ui. Alright, so here you can see that the covariance of xi tilde and vi would be equal to negative beta 1 covariance xi tilde wi plus covariance of xi tilde and ui. Okay, since we assume xi and ui are uncorrelated, then xi tilde and ui is also uncorrelated, right? Well, because xi tilde is some function of xi, if xi and ui are uncorrelated, xi tilde cannot be correlated with ui. Okay, and what is xi tilde? Xi tilde is xi plus wi. Therefore, covariance of this one would just be equal to negative beta 1 and variance of w, as xi and w are not related. Okay, so in this case, beta 1 hat would be equal to beta 1 plus, okay, here covariance is equal to negative this, negative beta 1, and the denominator variance of xi is equal to variance of x plus variance of w. Then you rewrite it. This is equal to variance of x divided by variance of x plus variance of w times beta 1. Here you can see that if the measurement error is severe, measured by the sigma w square. Okay, if this is big, sufficiently large, infinity, okay, then beta 1 hat would equal to 0, right? Then this would be very inconsistent. But if there are no measurement error, sigma w square is 0, then in this case, beta 1 hat is consistent. Beta 1 hat will goes to beta 1. Okay, therefore here we can show that if there's measurement error in X, we have the internal validity problems. How about Y? Okay, if we measure Y imprecisely, will we have any problems? The answer is no. If we have the measurement error in Y, actually, the estimator will still be unbiased. Okay, we are going to show these results in the form of exercise. Okay, so let's do the exercise. Now you can press the pause of the videos and finish this question first, and after you finish you can check the answer. Okay, this question is saying that if the regression model is like this, okay, but you imprecisely measure yi by yi tilde, which is the true yi plus some error terms wi, in which wi is iid, then the population regression equation will become like this. Okay, so first you are going to show that vi is equal to wi plus ui plus wi. This is very simple. In the midterm, if you don't know how to equate some variables, what you can do is to rewrite the given equation. Okay, in the question we know that, okay, yi tilde is equal to beta 0 plus beta 1 xi plus vi. Okay, we also know that, okay, yi tilde is equal to yi. Okay, what is yi? Yi is this, okay, beta 0 plus beta 1 xi plus ui, and you also add a wi here. Done, right? Yi tilde is equal to yi tilde, and here you can see that wi plus ui will be equal to vi. Question B, are the OLS estimator consistent? Okay, consistent means that whether the beta 1 hat is equal to beta 1. Well, you know that beta 1 hat is equal to covariance of xi and yi tilde divided by the variance of xi. Okay, here this is equal to beta 1 plus covariance of xi. Okay, and the error term is now ui plus wi. Okay, first of all, xi and ui are not correlated, and xi and wi is also not correlated because we assume that wi is iid. That means the covariance between wi and any variables are 0. Then in this sense, this is equal to 0. This proves that the beta 1 hat actually equal to beta 1, so the OLS estimator is still consistent. Here it shows that if we have a measurement error in y, there will be no problems. Okay. Then let's turn to next page. This is the third internal inverted problem, which is called simultaneous causality. Now again, you can try to pause the video and finish these questions.